Welcome again to our chemistry class. I hope you're all doing well. In the previous lessons, we discussed bond polarity, and today we will have a look at polarity of molecules. Objectives of our lesson. At the end of this lesson, you should be able to identify polar and nonpolar molecules, explain why some molecules are polar while others are not, and explain why a molecule may be nonpolar even if its bonds are polar. Polarity of molecules. The polarity of molecules depends on two factors: the relative electronegativities of the atoms in the molecule and the molecular shape. About the relative electronegativities of the atoms in the molecule, when electronegativities are different, we know that the bonds will be polar. And if the bonds are polar and the charges, the partial charges on each pole are separated, we get dipole moments. And then with a particular shape, the dipole moments may cancel out to give a nonpolar molecule, or they may not to give a polar molecule. Here we have the common molecular shapes. And the shape of a molecule, as we know, can be predicted from the bonding pattern of the atoms forming the molecule or a polyatomic molecule. I hope you remember how we determine molecular shapes using the valence shell electron pair repulsion theory. We have a linear shape. This is the first one we have here. This is the linear shape. We have a trigonoplanar shape. And in this shape, we have atoms which are symmetrically arranged. Here we have a trigonobipyramidal shape. Here we have an octahedral shape and tetrahedral shape. In all these five shapes, the atoms, are symmetrically arranged. And here we have the angular shape where the atoms may be symmetrically arranged, but the electron domains are not, because we have an electron domain here for the lone pair. It is the same with another shape like that of ammonia, for example, which is not also symmetrically arranged. Why? Because of the lone pair which is on nitrogen. Another example is that of water. Dipole moments and polarity. The polarity of a molecule is determined by measuring the dipole moment. And dipole moments occur when two electrical charges of opposite sign are separated by a distance. Suppose that here we have a positive charge and a negative charge. If the two opposite charges are separated by a given distance, then we get a dipole moment. Dipole moments arise from differences in electronegativities. As we said earlier, we said that when a molecule has atoms which contain different electronegativity values, then what we produce is the permanent poles. Here we have a partial positive hydrogen for our molecule of hydrogen chloride and a partial negative pole. And you can see that the partial positive charge is separated by the partial positive charge is separated from the negative charge by a certain distance, and because of this we have a dipole moment. And in chemistry we consider this dipole moment to be moving from the partial positive pole to the negative pole because electrons are withdrawn from the less electronegative atom, which becomes partial positive pole, and to the more electronegative atom, which becomes the partial negative atom or pole. So here we have an arrow showing the movement of our dipole moment from the partial positive pole to the partial negative pole. Molecules which do not contain polar bonds are nonpolar. If in a molecule there is no polar bond, then automatically the molecule becomes nonpolar. If we have chlorine molecule, for example, chlorine and another chlorine atom, the bonding pair is equally shared because we have a homonuclear molecule. So the molecule will be nonpolar because the bonds are also nonpolar. If molecules contain polar covalent bonds, they will be polar if and only if the dipole moment vectors on each molecule will not cancel out, and they will not be polar if the dipole moments do cancel out. And that is what is explained here. So we have two possible ways. A molecule may be nonpolar if it contains nonpolar bonds, and it may also be nonpolar if it contains polar bonds. Let us take the example of carbon tetrachloride, for example, with chlorine. Carbon tetrachloride with chlorine. We have carbon tetrachloride with chlorine here. We have another chlorine here. We have another chlorine and another chlorine to give us a tetrahedral shape. As you know, the electronegativity difference between carbon and chlorine is 0.5, and being 0.5, it means that we have two poles, a partial positive pole on carbon and a partial negative pole on chlorine, which is more electronegative. The electronegativity value of chlorine is 3, while that of carbon is 2.5. And you can see that the molecule we have here is symmetrically arranged. The atoms in the molecule are symmetrically arranged. To mean what? To mean that the dipole moments will all cancel out. We have a dipole moment moving from carbon to this chlorine, another one moving from this carbon to this chlorine, from the same carbon to this chlorine, and the same thing is also here, from the carbon to this chlorine. And the four dipole moments we have here, or the overall dipole moment here, is 0. Why? Because they are moving in opposite directions. So the dipole moment vectors on this molecule will cancel out to give us a nonpolar molecule. It means what? It means that even if a molecule may sometimes contain polar bonds, it is not always that it will immediately be polar. Sometimes if the molecule has atoms which are symmetrically arranged, we get a molecule which is nonpolar. Why? Because the dipole moment vectors will cancel out. A molecule containing polar bonds can only be polar if the structure of that molecule is not symmetrical. And here we can give the example of ammonia. ammonia, here we have nitrogen and hydrogen. Hydrogen, we have hydrogen here and another hydrogen in our shape which is not symmetrical. Why? Because of the lone pair we have here. So because if we consider, for example, another way of understanding better this is to consider where we have the center of negative charges. The negative charge, the negative pole, is here on nitrogen, which is more electronegative, and the center of the positive partial charges on each hydrogen will be where? It will be somewhere I'm going to show you, and we will check if the two centers will be in the same position or in different positions. Here we have the position of our negative pole, and if you consider the center of the three hydrogen atoms, you can find it here, somewhere here. So here we have a center of the partial positive charges, and here we have a center of the partial negative charges to show that we have a partial negative pole up and a partial positive pole down, with the two charges separated by a given distance, and because of that we get a net dipole. So the dipole moments in this molecule will not cancel out because simply the molecule is non-symmetrical. The atoms in the molecule are not symmetrically arranged, and then we get a polar molecule because first of all it contains polar bonds, and second, it doesn't have atoms which are symmetrically arranged. Let us have more examples. Here we have an image which shows two examples, and the first one is carbon dioxide. In carbon dioxide, you can see the dipole moments here and the two dipole moments which are moving in opposite directions. So the dipole moment vectors in these molecules which are moving in opposite directions, they will cancel out to give us no net dipole. We can also use the idea of centers of the charges. This carbon is the one which carries a partial positive charge. Why? Because it is less electronegative, and the oxygen atoms are carrying negative, and here we also have a partial negative charge. But what happens? If you consider the center of the two negative charges, you will find it to be somewhere here. And because of this, you can see it is exactly in the same space at the same point with the positive charge. So being in the same point, they immediately cancel out to give us a molecule which is nonpolar. So you can use the centers of charges or the dipole moments to explain why a molecule containing polar bonds is nonpolar. Here we have an example of a water molecule, and a water molecule is a very good example that we can use to demonstrate some of the physical properties of polar substances that I will tell you very soon. Here we have the dipole moments, and this time the dipole moments are moving in the same direction. The dipole moments are moving in the same direction, and this gives us a partial negative pole at one end of the molecule, and here with the partial positive pole and another partial positive pole, we get a center of the positive charges here. And this shows what? It shows that we have two poles in the molecule, the negative pole and the positive pole, showing that our molecule is polar. It is because of two reasons. We have polar bonds, oxygen-hydrogen bond is polar, and the molecule is not symmetrically arranged. So we have a net dipole moment because the dipole moments we have in this molecule, they are not cancelling out as they are not pointing in opposite directions. And the different colors you are seeing here, they are showing the distribution of charges. The red representing the positive charges, and this one with almost a gray color or the blue color with which is representing the negative charges. As I said earlier, water molecule is a good example to demonstrate how polar molecules behave physically. Sometimes if you take a ruler and rub it in your hair, it will be electrified, and if you put it closer to water which is flowing down, then as this one here we have an electric field, then the molecule which is polar will slightly bend towards the electric field. But if the molecule is non-polar and it passes near the electric field, then it will pass straight. This is something you can try at home. You take some water, you let it flow down, and you rub a ruler, a plastic ruler in your hair, and you put it closer to the flowing water. You will see what happens. But that cannot happen if you are using oil, for example, which is a non-polar substance. A simple definition of whether a complex molecule is polar or not depends upon whether its overall centers of positive and negative charges overlap. We have explained this. If they are in the same position, in the same space, then the molecule will be non-polar. But if they are in different positions, separated by a given distance, we will have a net dipole to give us a polar substance. And if the centers lie at the same point in space, then we have a molecule which is non-polar. If they are separated by a distance, we get a polar molecule. For a molecule containing similar bonds, the dipole moment is zero if charges are symmetrically arranged, and commonly it is with these shapes: AX2, AX3, AX4, AX5, and AX6. We all remember these shapes. And a molecule is automatically polar if it contains different polar bonds. If the bonds are different and they are polar, then the molecule will be automatically polar. If there are similar polar bonds that balance each other around the central atom, the overall molecule will be nonpolar because the dipole moments will cancel out. We have the example here: carbon connected to 4 hydrogen atoms. We have a positive pole, positive, 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 and the negative pole which is in the center. But because our molecule is symmetrically arranged, then the dipole moments will cancel out to give us a non-polar molecule. Here we have an example of a polar molecule. The shape is symmetrically arranged, but we have different bonds. So the dipole moment cannot cancel out because we have different bonds and different dipole moments. So when you have different bonds, and the bonds which are polar, the molecule is automatically polar because it has a net dipole. Now here we have the exercises. Classify the molecules below as polar and non-polar, and you explain your reasoning. We have a list of many molecules, and then you explain why the molecules we have here are polar or non-polar. First of all, you identify whether they are polar or non-polar, and you explain your choice. Thank you very much. See you for the next lesson.